Okay.
Are you ready?
Almost. Okay.
This is the Aldrin Cycler, which repeats every 2 1/7 years. It uses multiple gravity assists of Earth in order to repeatedly encounter Earth and Mars without spinning propellant.
Put here, here, here. So is this one? I keep it in this way, then I will. Okay. Okay.
Ready? Okay, last presentation of this evening session will be given by Mauro Pontani from the Department of Aeronautical and Electrical and Energy Engineering from Sapienza University.
Thank you, Chairman, for your introduction. This research addresses the hyperbolic rendezvous of the taxi vehicle with the Earth-Mars cycling spacecraft in the context of a new concept for Earth-Mars missions. So in the next slide, that is actually a movie from YouTube. We'll see the original idea. So you see in this,
This is the Aldrin
in this
Cycler,
animation,
which repeats
the
every
orbit
2
of the Earth
1/7
and
years.
Mars.
It uses
And in
multiple
green,
gravity
you
assists of
see
Earth in order to repeatedly
the
encounter Earth
cycling
and Mars
spacecraft
without
that
spinning
continuously
propellant.
travels
Our
between the
cycler
Earth
vehicle, the
and
Green
Mars.
Diamond, is boarded
And
by the
actually, you should
fly
notice
by
the
Earth.
relative position of these two planets.
After
So
5
after
months, the first
reaching
crew
Mars,
arrives at Mars.
the first crew
Cycler vehicle
that is on
does not
board
stop
the
at Mars,
cycler
so
can
it takes a
disembark.
smaller taxi
And
vehicle
then
to the surface.
the motion
cycler
of the
vehicle
cycler
navigates its trip back to the Earth to
continues
pick up
after the
Earth's
encounter
gravity.
with Mars. So when the two planets reach the same
2 1/7
initial
years
relative
after
initial
launch,
configuration,
the
there is
cycler
the
vehicle
second crew that
Earth
can
picks up
board
second crew
the
back
cycler,
on Mars.
and then the
Relative
traveler
positions
can
of
go
the Earth
home.
and Mars are the
And you
same
see
as the
now
initial Earth.
that after a few months, there is the second
The
disembark
second crew is
in
dropped
Mars.
off at
And
Mars
this
and
process
joins
can
the
be
first
repeated
crew.
several
The cycler
times.
vehicle continues on its way back to Earth to pick
So
up
this is just to illustrate the concept of the cycler architecture for the interplanetary travels. That means that basically there is a big, so yeah.
Okay. You have the pointer?
No.
It's here.
So basically there are three kinds of architectures for this kind of interplanetary transfers. And in these three architectures you can notice that we can have semi-cyclers when you have just a flyby at one of the two planets, in this case the Earth, in this case Mars, or a complete cycler like that we have seen in the animation. In this case we have two flybys at the two planets. This is occurs the schematics of the interplanetary transfer. The important thing is that while in the sphere of influence of the Earth or Mars, the trajectory is occurs a hyperbola. So in this case, this research is addresses in particular the flight between the Earth orbit and this cycling spacecraft. In particular, the taxi trajectory. So if we have a small vehicle around the Earth, we want to reach the cycler trajectory so that the big spacecraft can travel and lead the crew or the instrumentation toward Mars. So in this kind of problem we have two vehicles involved. A small taxi vehicle going from low Earth orbit to the cycler and a large cycler vehicle. The advantage is that once we have the cycler vehicle we can use of course a large cycler vehicle instead only a small taxi with a short term instrumentation or a life support system on board. So basically, however, this problem is challenging because the hyperbolic rendezvous at Earth must be done with a very high-speed vehicle, the cycler. And of course, if we have a cruise on board the taxi from the low Earth orbit to the cycler, one should also think about a strategy, an abort strategy, in the case that something goes wrong. So this is just the outline of this talk, and I will consider high thrust hyperbolic rendezvous and also low thrust hyperbolic rendezvous. In both cases, I will present optimized results, the optimal trajectories, let's say. For the high thrust hyperbolic rendezvous, there are several options. Instead, for low thrust hyperbolic rendezvous, I will present just an optimal trajectory. So for I trust hyperbolic rendezvous occurs, I'm using the usual impulsive thrust approximation. That means that I trust for short duration is modeled through an instantaneous change in velocity, like in this figure. So the objective is to find the optimal location, magnitude, and direction, and also number of the velocity impulses that lead the taxi vehicle to rendezvous with the cycler. Of course, since the cycler trajectory toward the Earth is known with a considerable advance, we can choose, of course, the orientation and the initial position of the taxi vehicle. That means we can choose the mutual orientation of the initial orbit of the taxi. This means that the rendezvous actually reduces to an orbit transfer. Okay, so also the initial spacecraft position, I mean the initial taxi position and the initial orbit of the taxi orientation, the orientation of this orbit can be chosen. In particular, the direction of the velocity impulse is defined through this angle delta that is taken from the local horizontal. So this slide just lists some of the analytical results found in a previous paper of about 8 years ago with regard to locally and globally optimal velocity impulse transfer from an ellipse and a hyperbola. And in this case, the assumptions were that we have an unspecified mutual orientation and time of flight for the initial orbit and the hyperbola. And also the intermediate arcs have these constraints. So there is a minimum periapse radius and a maximum apopse radius. So analytically, it was found that two kinds of globally optimal transfers exist. They are composed of two impulses or four impulses, depending on the energy of the hyperbola with respect to this value, this parameter. And in both cases, the sequence can be found analytically and includes a so-called infinitesimal impulse at infinite distance. That means that you can go farther and farther and at the last impulse, and also the overall transfer gets better and better. So of course it is a limited situation, but that means that you can go arbitrarily far, and also your transfer will require less and less amount of fuel. Moreover, I found also that there exists a locally optimal three-impulse transfer. These are theoretical premises for the current research. In fact, in the current research, we have considered the two-impulse, three- and four-impulse rendezvous trajectories in order to see in which case each of them is optimal. Okay, optimal means that requires less amount of fuel. That is the least possible delta V budget. So the rendezvous point in our investigation is identified through the time delta TP spent after the periapse pass of the cycler. Okay, so this is the time right after the periapse of the cycler, and identifies the point at which rendezvous can occur. And the problem is, for the two impulse rendezvous, is in finding the optimal location, magnitude and direction of the two impulses, the first one and also the second one, such that this is minimum. And this plot just illustrates that the first impulse is applied at apopse in this case for this initial position up to about 1 hour after the periapse pass, and then must be applied at periapse. So here you can see what I mean. So if the rendezvous occurs sufficiently close to the periapse of the hyperbola, the periapse of the hyperbola is here, it's just in the horizontal position. If the rendezvous occurs sufficiently close, the first impulse must be applied at apopse and the second here at this point. Instead, if the rendezvous point is sufficiently far apart from the periapse, the first impulse is at perigee, and it is what we see here. Okay, this is the apogee position. This is the perigee position. Yes. And here we have also the times of flight for each case. And here you can see the delta V budget for this transfer, depending on the rendezvous point. Okay, so you see that actually the delta V decreases as the rendezvous point is farther and farther. And the optimal point in this case is the maximum distance, the maximum allowed distance. Occurs. I've talked about the need of an abort strategy. In fact, if we have a crew on board the taxi vehicle, basically we would like to have some rescue strategy, let's say. So if we imagine that the first impulsive bar is performed, and then after that one realizes that there is some problem on board, of course we would like to plan some rescue operation, and the way of doing that is to inject the spacecraft, the taxi with crew on board, into an ellipse after the first impulse, not to inject this into an hyperbola. And so a suitable board strategy is to include this constraint on the elliptic intermediate arc with a maximum up-ups radius of 400,000 kilometers. So again, also in this case, the rendezvous point is identified through this time spent after the periaps pass. And you can see here, again, the optimal location is the up-ups here, and periaps for points, farther points. So here you see the delta V budget. You can see that up to this point here, the constraint on the up-ups radius of the intermediate arc, that means the abort strategy constraint, is not active. So in this short range, up to this time, the situation is exactly the same as before. Then after this point, the constraint on the maximum up-ups becomes active, and you see that this has a real implication on the overall delta V. So in the presence of an abort strategy, the overall delta V increases a lot. And there exists an optimal point here. So there exists an optimal point where you can inject, where you can perform the rendezvous, and it is corresponding to this time. So in this right figure, it is the point is after 5 hours, and you have the first impulse and the second impulse. So another suitable option is to perform the rendezvous through 3 maneuvers. And in particular, we have now, on the basis of the theoretical results found in the previous slide, if we set up these constraints on the minimum periaps radius and this constraint on the maximum up-ups radius, we can find this locally optimal transfer, let's say locally optimal rendezvous trajectory that includes a first tangential impulse at periaps, a second tangential impulse at up-ups, and a third tangential impulse at the periaps of the incoming hyperbola. And this takes, however, about 30 days, so it's not suitable for crews, of course, but maybe for instrumentation. However, you should notice that the delta V has this specified value for this kind of transfer. Of course, this is maximum up-ups radius, and this is the minimum periaps radius. Sorry, no, this is not the minimum periaps. The minimum periaps radius constraint becomes active in this other impulsive rendezvous case. In fact, lastly, we have considered also the case of 4 maneuvers, and in this case, again, we have this general result that if the point at which the rendezvous occurs is identified by this time, then the 3 impulse rendezvous is globally optimal. Otherwise, we have this range in which the 2 impulse rendezvous is globally optimal. Instead, if the point at which the rendezvous occurs, the 4 impulse rendezvous is globally optimal. And this is the case when the 4 impulse rendezvous is globally optimal with all the delta V's and also the delta V, the total delta V. Of course, I'm talking about the rendezvous without any abort strategy here. So there are 3 cases depending on the ejection point along the incoming hyperbola. And this is the picture of this kind of rendezvous. So you can see the first impulse is tangential to reach the maximum up-ups radius. Then here you have a a tangential impulse in the direction opposite to the motion to decrease the periapse to the minimum allowed value, and then here you have the third impulse at this point, and then finally the fourth impulse at this point. So the second option that can be considered is the use of a low continuous thrust. So this case, of course, is completely different from the previous one because we cannot use at all the impulsive thrust approximation. Instead, we have continuous thrust here, and the problem is in finding the initial point and the final point at which concludes the rendezvous trajectory, and also the thrust direction time history, that is a function of time, of course, such that the time of flight needed to perform this rendezvous is minimized. We can use two equation sets. There is a reason for that, because there is the first equation set that includes the radial component of the velocity, the horizontal component of the velocity, and the radius. And there is also a second equation set that apparently it is more complicated, that includes the parameter of the orbit, the instantaneous parameter of the orbit, the instantaneous eccentricity, and the true anomaly. These are the so-called Gauss equations for the orbit elements, and they are much more complicated. However, they have an advantage, as we will see shortly. This is the complete definition of the problem. If you consider the necessary conditions for optimality for equation set A, you of course obtain the Hamiltonian, the adjoint equations, and also the very important thing is that you can always express the thrust pointing angle as a function of the adjoint variables, like in this way here. If you use the equation set A, you must include also parameter vector, okay, and parameter conditions. So without going on with details here, the second set of necessary conditions for the equation set B does not include any parameter set and has an Hamiltonian that is much more complicated. But if you write this Hamiltonian in this form, you can always write again the thrust pointing angle as a function of these complicated functions HRB, HT. And in any case, you can have an explicit expression of the thrust pointing angle as a function of the other quantities. Also in this case, you have the adjoint equations, of course. So once we have these necessary conditions, we need, of course, a numerical method of solution. And there are many. I will not spend words on the known things. In the sense, there are the classical methods and the heuristic methods. The difference is in the need of guess. In fact, we need guess for the deterministic methods. We do not need any guess for heuristic methods. However, they are more precise. The first are more precise. In this kind of a method that is called the indirect heuristic method, we join the analytical conditions for optimality and the heuristic technique. Basically, this method considers the initial values of the adjoint variables as unknown parameters, so that we can express the control as a function of the adjoints that are inside these functions. So once the initial values of the adjoints, the optimal initial values of the adjoints have been determined, one has also the optimal control time history, and the boundary condition violations are all minimized to 0. This means that we are minimizing the final conditions on the state, but also on the adjoints. So for the equation set A, we have this small, really reduced parameter set, and for the equation set B, we have even more reduced parameter set. Just the first value of the Lagrange multiplier lambda 1, the second initial value of the adjoint lambda 2, the initial value of the true anomaly, and the time of flight. So if we use the indirect heuristic method, we have in the end, of course, with canonical units, with 100 particles and 1,000 iterations, we obtain, and with these propulsive parameters, we obtain convergence only using equation set B. In fact, using equation set A, 10 attempts were not sufficient to find any convergence. This is the thrust pointing angle, it is the thrust direction in time. With this thrust direction, we have finally the injection, the rendezvous with the very precise final conditions, and it is the minimum time that is equal about to 40 hours. And now in this other slide you can see trajectory. So there are the initial trajectory is the GTO, and after several orbits around the Earth, there is the rendezvous point. The rendezvous occurs at a distance of 100,000 kilometers, and these are also the velocity components. You see the radial velocity and the horizontal velocity time histories. This slide just reports parameter and eccentricity time histories. This is a very interesting thing from the optimal control point of view, because there is an apparent result from this investigation, that is the equation set A. We can reconstruct, however, retrieve, however, the Lagrange multipliers for the first equation set. You can see here that we have a really abrupt variations for one of these Lagrange multipliers. Instead, if we use the adjoint variables and the equation set B, we have really smooth behavior for these variables. So this occurs an indication of hypersensitivity of the problem if you use the first equation set. And in fact, we can confirm this through numerical experiments, just using as very small perturbation of the initial values with respect to the optimal ones. We have these values for the objective function. The objective function in this case just includes the overall constraint violation. So if you use the equation set B, you have really not sensitivity to the initial values of the Lagrange multipliers that are smooth. Instead, in this case, a small variation in the initial condition implies a big variation in the objective function, and this prevents convergence. So I'm going to the conclusions. So in the first part of the talk, I consider the I-trust hyperbolic rendezvous. There are several options here indicated with the related delta V budgets. And however, depending on the time at which the rendezvous occurs, we have that the 3 impulse or the 2 impulse or the 4 impulse is globally optimal. And the second important consideration is with regard to low-thrust hyperbolic rendezvous. Although we have used optimistic propulsion parameters that will be achieved probably in the next 1 or 2 decades, we have that the final mass ratio is this. So we need just the 17% of the initial mass to perform this rendezvous, starting from the GTO orbit. And similar I-trust propulsive system would require, to have the same performance, would require at least this effective exhaust velocity. And this exhaust velocity for I-trust propulsive system is completely beyond the current technological capabilities. So this means that while it is really likely to have some low-thrust propulsive system capable of doing this, it is completely unlikely to have in the next decade something that has this performance. And this is the reason why low-thrust propulsion can be really interesting in this application. And that concludes my presentation. Thanks for your attention.